Just do a short review here just to kind of recap some of the big ideas in this module. So one of the things we did was we did operations with rational expressions. Remember, for multiplication division, you can cancel common factors diagonally and within the same fraction. Adding and subtracting, you have to have a common denominator. This is really important too. If it's not an equation, you're not solving for x, so you're just simplifying, combining like terms. Okay, so let's do an example here. This is subtraction. I need a common denominator. So I'm going to multiply by my common denominator. Sorry, this one should be plus 2. And this one we're doing x minus 2. Okay, so I've got 3 times x minus 2 minus x times x plus 2 over my common denominator. Okay, do some distributing and combining like terms. So we're going to get 3x minus 6 minus x squared minus 2x. Okay, here I'm going to get negative x squared plus x minus 6. Again, anytime I want to factor, it's kind of nice to have a positive x squared term. So I'm going to factor out my -1. So I've got -1 times x squared minus x plus 6. Double checking, making sure I'm right there. Yep, okay. And this one, you guys, I don't think is actually going to factor because I have to multiply to be a positive and add to be a -1. And I don't think that's going to happen. So this is going to be my simplified expression. You could either leave it as this or as this. Okay, and if they do ask about specifying what x cannot be, remember that x could not be -2 or +2. Okay, when I have complex fractions, remember that exponent of -1 is really x times 1 over x plus 1. I can think about that as x over 1 too. Let me write that on the same level. Okay, and then over here I have 1 over, sorry, this should be 2 over, the -1 is just on the x. Okay, if it was in parentheses, then the 2 would go on the bottom. Okay, so we're going to simplify the numerator and denominators here first. So on the top, I'm just going to get x over x plus 1. Here, I need a common denominator to add, so I'm going to multiply this one by x and this one by x plus 1. So we've got 2 times x plus 1 plus x squared over x times x plus 1. Okay, so this turns into multiplication. So I have x over x plus 1 times, this guy's going to flip. I'm going to do a little combining of like terms there. So I've got 2x plus 2 all right, so these guys I can cancel. And I'm going to get x squared on the top. X squared plus 2x plus 2. Let's see here. I don't think I can factor this. Numbers that multiply to be 2 that add to be 2. So this is going to be my simplified expression. All right. Okay, now if we are asked to solve, there's going to be an equal sign. It's really important that we check answers so that I'm not providing extraneous solutions as my answers. So I need to get, this is where I want to multiply by my LCD. So my LCD here is x plus 2, x minus 2. So we're going to multiply every single thing by that. So I'm going to write it out down here, you guys. X plus 2, x minus 2, and then equals 2 times x plus 2, x minus 2. Okay, so I just rewrote that multiplication down here. So this is that clearing fractions process. Cancel, so I have 3 times x plus 2, which is 3x plus 6. Here I'm going to get my minus 2's to cancel, so I have minus x times x plus 2. And then over here equals 2 times, I'm going to do a little distributing. Let's see, I'm going to get x squared minus 4 over there. Difference of squares. Okay, a little more distributing. Equals 2x squared minus 8. Okay. I want to set my denominator, or set one side equals 0, so I'm going to add everything over here. So let's see, we get 3x squared, right? Then here I'm going to add, I've got x, so minus x, and then I'm subtracting 6, so I get negative 14. Sorry, that's a little crowded. All right, this one is going to be a reduce and bottoms up. 3 times 14, I think it's 42. Yep, okay. So I've got, so numbers that multiply to be 42 that add to be negative 1 are negative 7 and 6. Okay, reduce and bottoms up. So here, bottoms up with the 3. And x plus 2. Okay, so to solve, now I'm going to set 3x minus 7 equals 0 and x plus 2 equals 0. So x is 7/3 or negative 2. Back to the beginning, what x could not have been was what would make my denominator equal 0. So this was x could not have been negative 2 or 2. So this solution is extraneous. And so just x equals 7/3 is our solution. All right. Last part of the unit, we learned how to graph functions. Helpful to factor them so we can see wholes, common factors, asymptotes, etc. a little bit easier. So I'm going to factor this one. Let's see, x minus 2, x minus 3. Okay, so horizontal asymptote, I had the same degree, so the leading coefficients are 1 and 1. Vertical asymptote, I do have a hole here, so at x equals 2. And then vertical asymptote is the other piece that would make my denominator 0, which is going to be at 3. Slant asymptote, if there is a horizontal asymptote, there is not going to be a slant. Okay, so let's graph. Okay, so one thing about the holes, you guys, is we can actually find the coordinates of the, right now I know the x coordinate is 2. We can also find the y coordinate. So if I were to cancel those, I have x over x minus 3. So if we were to plug in 2, so I'm going to have y equals. So here I'm going to get 2 over negative 1, which is negative 2. So that means the hole has coordinates 2, negative 2. All right. Okay, so let's graph some of this. So we've got, so let's see, horizontal asymptote at y equals 1. X equals 3 is a vertical asymptote. Okay, the hole, 2, negative 2. So I'm just going to show, oh, sorry, that's, that's the downside of pen. Sorry, not that one. Here's my hole. 2, negative 2, so we just show that with an open circle. So this is where I have the T, my graph's either going to be here and here or here and here. Typically it is going to connect through the hole, so most likely here. Let's put our intercepts as well. We didn't calculate those. So x-intercepts, we are going to set the numerator equals 0 after the hole has already been done. So it's just x equals 0. So 0, 0 is an x-intercept. Y-intercept, that's where we plug in 0 for everything. So I have 0 times 0 minus 2 over 0 minus 2 times 0 minus 3. I'm going to get 0 on top. So 0 is our y-intercept. So 0, 0 for both x and y. Okay, so I know the graph down here is going to go through the whole like that and hug those asymptotes. It's going to be up here somewhere. It might be good just to put one other point in here. So my vertical asymptote's at 3, so let's maybe plug in 4. So I'm going to find what is f of 4. So I'm going to plug in 4 into my original equation. So we've got 4 times 4 minus 2, and then divided by 4 minus 2 times 4 minus 3, which is 4. So 4 is the next point. So there was 4, 1, 2, 3. Oh, sorry. 1, 2, 3. There we go, 4. So this guy is going to look something like this. Okay. All right. Then we have writing a rational function given some information. So this one, they want us to have a horizontal asymptote at 0. So that means degree on bottom is bigger. Vertical asymptotes and no holes. Okay, so we have vertical asymptotes at 2 and 3. So we know on the bottom it's going to be x minus 2, x minus 3. I just want the degree on the bottom to be bigger, and I don't want any horizontal asymptotes. So right now I have a degree of 2, so I could just put a 1 on front, or I could put like an x. Doesn't really matter, okay? That's fine. So there's more than one option. So there's no other specifics here. That is just fine. Okay, so one thing, how do we get no holes? No common factors in the numerator and denominator. Now this one, no vertical asymptotes. We had an example like this earlier in the notes, but denominator is going to be x squared plus something. So because then I can never make it equal 0. If it's just x squared, 0 would make it be 0. But if I have like x squared plus 1, then I can't make it equal 0. So I'm just going to put plus a number. I usually do 1, but you can do whatever you want. All right, guys, and that is it. The last thing I would just say is slant asymptotes. I'm going to add this note in here. Totes is long division to get. And that happens when numerator is 1 degree higher than the denominator. Okay, that is it, you guys. Thanks so much for watching.